Chemical research of today is focused on function over structure. Chemists today are asking questions like how does this happen over questions like what does this look like. Questions about function are generally much harder to answer through experimental techniques alone, and so theoretical modeling has become an essential supplement. Theoretical models exist everywhere in chemistry. They can range from the ball and stick models of simple molecules to complex computer models of intermolecular interactions.
Are you ready to learn about these three men who changed the world of chemistry forever? Yeah, you are!
In the 1960s, three scientists, Dr. Arieh Warshel, Dr. Michael Levitt, and Dr. Martin Karplus, began their work on theoretical modeling. Warshel worked with Levitt in the Weizmann Institute of Science in Israel to calculate the behavior of molecules with computer programming. They employed classic Newtonian physics in their early work. At the same time, Karplus was working towards developing computer programs that could simulate chemical reactions in his lab in Harvard. He set out to harness quantum physics to view physical reactions at the microscopic level. Dr. Warshel later joined Dr. Karplus in his lab for postdoctoral research, and in 1972 they published a paper entitled Calculation of Ground and Excited State Potential Surfaces of Conjugated Molecules in the Journal of American Chemical Society. This work combined both quantum and classical physics in describing the chemical behavior of specific molecules. Dr. Warshel once again collaborated with Dr. Levitt to repurpose their programs to observe enzymes. They knew the shapes of these enzymes, but they knew very little about their functions. They discovered that they couldn't understand the behavior of the enzyme without considering the effects of the surrounding molecules that the enzyme is suspended in this case, water. The collaboration between these three scientists led to the revolutionizing of the role of computer-based modeling in chemical research. Their work was awarded the 2013 Nobel Prize in Chemistry for the development of methods using both classical and quantum mechanical theory to model large complex chemical systems and reactions. But why were these two chemical models brought together? Classical models describe atoms or groups of atoms and their structure. Classical physics has simpler calculations and can model very large molecules but can't simulate chemical reactions. The quantum chemical model targets the electrons and the atomic nuclei. It can simulate chemical reactions, but requires enormous computing power to do so and can only target small systems. The 2013 Nobel laureates developed combined models that use quantum chemical models to define the central part of the chemical system.
They then linked this part to a surrounding, which they modeled with classical particles such as atoms or groups of atoms. This combined model was embedded in a dielectric medium such as water to show how two regions can be made to interact physically. These two models, both with different representations, were thus brought together to provide the whole picture. The first step in developing such multiscale modeling occurred in Karplus and Warshel's study of complex biomolecules. So, electrons exist in different orbitals, which are probable paths around the nucleus of an atom. Bonds between atoms occur upon the transfer and sharing of electrons upon the overlap of these atomic orbitals. Two interactions that Karplus and Warshel observed in their study of large molecules were sigma and pi bonds. Sigma bonds occur in the overlap of atomic orbitals from end to end. Pi bonds form upon the side-to-side overlap of atomic orbitals, along a plane perpendicular to the axis connecting the nuclei of the atoms. Karplus and Warshel constructed a computer program to determine vibration spectra and thus the interactions between the atoms of the chosen molecule. This was accomplished with less strain on the computer by modeling sigma bond electrons and nuclei with a classical approach, while pi bond electrons were modeled with quantum chemical approaches. The successful hybrid method of describing complex chemical systems was first restricted to flat, planar molecules, due to the fact that natural symmetry separates both the pi and sigma bond electrons. So Karplus and Warshel needed a further modified approach that could model more complex systems. This was shown in their study entitled Dielectric Electrostatic and Steric Stabilization of the Carbonium Ion in the Reaction of Lysozyme. They learned that in order to understand how a lysozyme breaks down polymers, they had to model only relevant parts of the system that held the majority of the chemical reaction with quantum mechanics. The rest of the system had to be modeled with classical molecular mechanics. Thus, the quantum modeling and classical molecular mechanics hybrid streamlined the process of modeling complex chemical systems by focusing in-depth and more work-intensive quantum physics on only select locations in the system where chemically significant events occurred. This streamlining has created faster and more efficient computer modeling for very complex molecules and systems. With the advent of such a versatile hybrid modeling tool, the computer became an essential part of the chemist's toolbox. As chemistry continues to advance, our methods of understanding are evolving at a breakneck speed. Who knows what the future can hold? Thanks for watching.